Hello, I'm Chase, and this is my Physics 2211 lab, Lab 1. So, I'm going to start off by introducing the lab. So, the purpose of this lab is to observe the movement of an object at a constant velocity and construct a computational model based on the movement of said object. So, for my lab, I decided to use an expo marker and roll it along the side of a meter stick. So, it rolled parallel to said meter stick. It's allowed for the calibration of distance over time in the tracker application. And I took the video and put it in tracker and used the tracker to determine the position of the marker at each time interval. So between each frame, I could determine the time that passes, and the distance that it passes in each frame I could use to create an average velocity for the overall function. And I used the calculated average velocity to create a computational model in Python of the marker. So the distance that the model traveled in real life, I created a model in Python to mimic said data, and I compared to the real data. As you can see in the bottom right, I have a computational versus experimental data. So the red line is the computational model, and the blue line is the real data. So as you can see, they start separating towards the end as time goes on, and I will explain why towards the end of my presentation. So assumptions that you need to do this lab is that the velocity is constant. This will allow us to assume the position varies linearly with time. And second, we will have to assume that friction between the ground and the marker is negligible, so that no force is acting on the marker in the x direction. Or I should say that the sum of the forces acting on the marker in the x direction add up to 0. So some math or justification is that Newton's first law of motion is an object stays in motion unless an object in motion stays in motion unless acted upon by an outside force. Since we assume that there are not outside forces acting on the object, then we can also assume that the marker's velocity is constant. Therefore, we can use the position update formula because F net is constant, is at 0, and we can then use the equation RF equals RI plus the average velocity times delta t, and we can use that to determine the position. We can use the position update formula to determine the average velocity by reverse engineering this. So here's a little snippet comparing my tracker to the computational model. As you can see on the left-hand side, the computational model is linear, while on the top right of the tracker model, it starts to curve a bit, and it's not as linear as the computational model. This is because the computational model uses an input velocity from a starting position, therefore it's always going to be linear. Well, in tracker position, it's actually not linear because I'll explain why in a bit, but there's actually, yes, there are forces, so that there are some assumptions that we made that are technically false, but it's, in order to use this model, we had to assume that the friction force was negligible. So this is our data. It's written in scientific notation for the middle columns and the time columns. So they actually, as you can see back here, our initial position for the tracker model is a little behind the coordinate plane. So this caused our initial position for the x location to be slightly negative, which would be reflected in the data here, as you can see in the bottom left. And then, yes, this is our data, and these are the two graphs, and this is the program. I gave its initial position, which is negative, as I discussed earlier, and the velocity. And what we can conclude from this is the computational model overshot the actual model due to the frictional force actually causing deceleration. And our results support that Newton's first law is consistent with the data. So some source of errors: the marker was rolled at an angle, so due to the slight angle, this would decrease the velocity in the measured direction, and we ignored the frictional force, which would decrease the velocity overall. So what if, when you analyze the data, you had a choice about the orientation axis? Let's say you flip the negative x-axis and the positive x-axis. Well, this would just change your signs. Ultimately, your computational model would just be in the negative direction instead of the positive direction, but all your data would be technically right. It would be similar to if you drew an FBD with different respective variables, with different respective directions. And then my observations that can be predicted well with your computational model is that many forces are acting on the marker, but there are too many to count, but they all add to 0. This is our assumption. This is because the marker is assumed to be at a constant speed. And that's it. Thank you.